Hey guys, welcome back to another chemistry lesson here. We're going to be talking about something called the ICE method today. ICE stands for initial, change, and equilibrium. Now, it's a way of organizing your information to make complicated equilibrium expressions easier to solve. So, for example, we got two SO2s in gas. We've got O2 as a gas, and it's in equilibrium with two SO3s. So there's our balanced equation. It's all in equilibrium with each other. Here's the information you know. Initially, you've got 2 moles of SO2, 1 mole of O2, 0.1 moles of SO3. You know it's in a 15-liter container. So you let it sit for a while, and at equilibrium, there are 0.2 moles of oxygen left. What is your equilibrium constant? Now, there's a lot going on in this question, right? You've got 3 things initially. You've got the size of the container. You've got one of the things at equilibrium. And you've got, from all this mess of things, you've got to manage to find the product, or sorry, not the product constant, it's the equilibrium constant. So we need a way to organize this so it makes more sense, so it's easier to work with and do the math. So I rewrote the question up here. Same question, no difference. But I've drawn my ICE chart below. So you can see I've got initial, change, equilibrium, ICE. If you just want to write ICE when you're setting these up, that's totally fine as well. So let's start with SO2. How much do we have initially? Now, these ICE charts always work with concentrations, right? And so I had 2 moles of SO2 in a 15-liter container. Ugh, that was ugly. That's much better. So let's grab my handy dandy calculator over here. These might get a little complicated later on, so I'm just going to use the calculator on my an actual calculator, not the one on the screen here. But you can still follow along. 2 divided by 15. 0.13 repeating. So that is my initial concentration of the sulfur dioxide. And of course it is in molarity, moles per liter. And I can do the same thing for oxygen. Oxygen would just be 1 over 15 liters. So this is the SO2. This is the O2. So 1 over 15 equals 0.06 repeating. All right. And I've got sulfur trioxide, and I've got 0.1 moles of that. And that's still in a 15-liter container, which means it's at 0.006 repeating. All right, so that's all of my initials. They gave them to me, so it wasn't too bad. I just had to divide by liters. Now, what's the change going to be? To figure out how much it changes by, well, we don't actually know what the change is yet. So we look up here. 1 mole of oxygen makes 2 moles of sulfur trioxide when it combines with 2 moles of sulfur dioxide. So what this means is, well, first of all, what's getting bigger, what's getting smaller? If you take a look up here, we've started at 1 mole of oxygen, we've gone down to 0.2 moles of oxygen, so we're definitely using up our reactants, which makes sense. Usually that's the case. Sometimes it goes the other way. Like if I gave you 0 reactants and just a ton of sulfur trioxide, you might see it go backwards. But in this case, you can tell from the numbers, we're going to be using up oxygen. So oxygen is going to go down, which means sulfur dioxide is going to go down. Our reactants are going to go down together, and we're going to form sulfur trioxide. How much? We don't actually know. And so what do we do in math when we don't know something? Well, we give it a variable. We're going to call this x. So oxygen is going to go down by x amount. Now, if I compare oxygen up here and sulfur dioxide, you can look at the mole ratios and be like, oh, for every oxygen I use up, I would have to use up 2 sulfur dioxides. So it doesn't change by x, it changes by 2x. And the same for the sulfur trioxide. You can see it's got a 2 there for its mole ratio, which means I'm not making x of it, I'm making 2 times x, because I'm making twice as much of it. So the x is just for how much our change is, and that's kind of what we're going to figure out here. But you just call it x for now, and put the mole ratio in front as a coefficient to show how much it's getting bigger or smaller. Now I need to know something at equilibrium here. Well, I don't have to. We'll look at that later, but it's much easier if you do. And luckily for me, I know there's 0.2 moles left. Well, I don't work with moles. I work with concentration. So 0.2 divided by 15. And that's for what, O2? For O2. So at equilibrium, O2 is 0.0133 moles per liter. And now if you look at that middle column here, we've got all the information we need. We know we started at 0.066, we subtracted something, and we ended up at 0.0133. You need to find what x is. So some basic algebra here. Subtract 0.66 from both sides. So I get 0.0133 minus 0.06, repeating. And I get negative x equals negative 0.0533. All right. So now I know what x is. Positive x is positive 0.533, which means I can find everything else at equilibrium. I now know what x is. So I could take that x and I can plug it in there and I can plug it in here. So what is 2 times my x? 0.0533 times, 0.0533 times 2. So it's about 0.1066 if I times it by 2. So I have to take this number and add. So I'm going to go 0.0066 plus 2 times whatever my x was. So I do 2 times x, I add 0.0066. At equilibrium, this one's going to be 0.1132. And I can do the same with my sulfur dioxide. I'll do it in a different color so it stands out a little bit here. Let's do it in red. I take 0.133 minus 2 times 0.0533. Sorry, I had to write with my left hand. It's on the far side of my screen there. 0.133 minus 2 times 0.0533. All right, so this one at equilibrium, I'll go back to black so this chart looks nice and even. 0.0264. Okay, now that I know all my equilibrium ones, I can calculate Kc. Because it's products. Oh, that's not an S. Concentration of SO3 squared over reactants, products over reactants. And of course, those ones are squared because of the mole ratios, right? You look at the mole ratio and that's how you get your power there. So you just, well, do I have another? I do have a blank slide here. I'm going to use the blank slide. Let's rewrite this real quick. All right. Plug in what I know. I know SO2 is 0.0264. I know O2 is 0.0133. And it's not squared. Whoop, dropped my marker. Ugh. And what else do I know? SO3 is 0.1132 squared. All right. Now, the trick to these ones, because there's a lot going on here calculator-wise, do the bottom first, write down your answer, then do the top, write down your answer, and then solve it. So my calculator, I'm going to punch in 0.0264 squared times 0.0133. And it gives me 9.27 times 10 to the negative 1, 2, 3, 4, 5, 6. We just double check that. It's 0.0264 squared times 0.0133. Yep. 1, 2, 3, 4, 5, 6. Perfect. Yep. And then I'll do my top one. 0.1132 squared. I'm just going to write this one out because it's not too bad. So to do this, I type in my calculator 0.0128 divided by, and then here's the important one, guys, divided by open brackets, 9.27 times 10 to the power 6 minus, close brackets, equals. If you do not close that bracket, or if you don't use brackets here in your calculator, you're punching in 0.0128 divided by 9.27, and then you're timesing by 10 to the power negative 6. Your answer ends up as 0.00000001, because what you've actually done is you did this divide, and then you times your answer by 10 to the negative 6. And that is not what you want to be doing. So make sure you use the brackets in there. It's really common for people to have all their math right to this step, have everything shown properly, and then just have the wrong answer because they didn't punch it into the calculator correctly. So be careful with that. Make sure you use the bracket button on your calculator to put the denominator in brackets. All right, so that's one example. Let's look at another one here. Nice, easy formula, right? 2 ozones turns into 3 oxygens. All right. And we don't have to find our concentrations. They're telling them to us. Initially, ozone is 2 moles per liter. At equilibrium, ozone is 1.75 moles per liter. So we've gone from 2 down to 1.75. Not bad. What is the concentration of oxygen at equilibrium? Okay. Well, what's our starting for oxygen? They don't tell us. So what do you do if they don't tell you? Well, it's not a trick question. If it's not told to you, if they say, hey, we have 2 moles per liter of ozone and nothing else, that means you had nothing else. There was 0 oxygen. If they don't tell it to you, it's a 0. So it's not a trick question. Just remember that, hey, if this is what you got initially, that means you don't have anything else. So we can put our mole ratios in here. We're using up the ozone, obviously. So we're using it up. And the mole ratio for ozone is 2. Oxygen we're going to be creating, because it starts at 0, we have to make it. Its mole ratio is 3. So whatever our change is, we're going to get rid of twice that change for ozone, and we're going to triple that change to see how much oxygen we made. So we've got this full line finished. Let's write it out. We started at 2. We got rid of 2 times something, and we ended up with 1.75. So you want to solve this. You subtract 2 from both sides. 1.75. Well, I didn't type in at all. 1.75. My calculator is frozen. 1 point. There we go. Minus 2. So I have negative 2x equals negative 0.25. To get x on its own, you divide both sides by negative 2. And my final answer here, I'll do it in a different color because I kind of ran out of room. (0.125). So how much oxygen do I have? Well, I know what x is now. I have 3 times 0.125. So I have if I punch it out of the calculator, 375 moles per liter of oxygen. That is the concentration of oxygen at equilibrium. Now, these ones haven't been so bad yet. Let's make things interesting. Here's an equation. We got 3 things. I got 2 hydrogen iodide turning into hydrogen gas and iodine gas. So it's just breaking down. Kc, our equilibrium constant, is 0.16. So I already know it. That's nice. We know initially there's 0.01 moles per liter of hydrogen and iodine. So I wrote that in for you. And it doesn't say anything about hydrogen iodide, so we're going to assume 0. What are the concentrations of everything at equilibrium? Now, this one, a little tricky, because we don't know anything about equilibrium yet. Now, I know what my change is going to be. I started at 0, so I'm going to have to make some hydrogen iodide. Now, this is a weird one, right? Hydrogen iodide is our reactant. Normally, you'd be like, aren't you using up reactants? Well, I got 0 of it, so I definitely can't be using it up. So this is an equilibrium, right? Things can go both ways. If I've got nothing on the hydrogen iodide side, I have to be creating it. And its mole ratio is 2. which means if I'm creating reactants in this case, if this reaction is going in that direction, then I'm going to be using up my hydrogen and using up my iodine. So at equilibrium, I would have, well, 0 plus 2x is just 2x. I would have 0.01 minus x and 0.01 minus x. Now I look at these equilibrium numbers, and this puts me in a real good mood. Not because the math is easy, but because it's easier than it could be. If these two are identical, there is a math shortcut. And I'll show you what I mean by that in a second. So I've got Kc. I can write out my equilibrium formula. Oh, I have all my stuff here. I didn't mean to have that up already. I started doing it a hard way. I'm going to do it an easier way for you guys here. I forgot about the math shortcut, and I did it the long way. Then Mr. Shredder came and said, I think I did something wrong. And Mr. Shredder came up and kicked me in the butt and said, you're doing it the long way. So, products over reactants, H2 and I2. There's my products. Over reactants was HI. And of course, HI is squared. All right, so let's punch in what we know. Well, I know Kc. It's 0.16, right? They told me that in the question. It's right over here, top corner. I know my equilibrium for HI is going to be 2x. So I'm going to have 2x squared. And I know H2 and I2 are both 0.01 minus x. All right. For all you pre-cal friends out there, math nerds, I know what you're thinking. We're going to have to FOIL this, right? First inner, outer, last, do all the factoring stuff. We're going to have to move the x squared over. Oh, man, this is looking like a quadratic equation. Gross. And there are times where you're going to have to use the quadratic equation to solve these. Today is not that day. Remember how I said, if those two are identical, there's a math shortcut? Here you go. These two are the exact same number, right? Which means I can write it as 0.01 minus x times itself, which is squared. So I've got something squared over something squared. I really, really don't want to do the quadratic equation, so why don't I do this? Square root this side, square root this side. This will get rid of all of my squares, and at the same time, it'll get rid of my quadratic equation. So let me just erase this awful quadratic equation. So I'm going to have, what is the square root of 0.16? Square root that, 0.4. I'm going to have 0.4 equals, well, all I have to do, if I'm square rooting squares, the squares cancel out. That's all you got to do. So I'm left with 0.01 minus x, and I'm left with 2x. Now that is much easier to do. Times both sides by 2x. So I'm left with 0.8x equals 0.01 minus x. All right, well, I need to get all my x's to one side, so let's add x here. And I'll have 1.8x. And now to get x on its own, divide by 1.8 on both sides. 0.01 divided by 1.8. And x equals 0.0055 repeating. So am I done? No. I need to know what these numbers actually are. But that'll be easy now because I know what x is. I know x is 0.0055 repeating. So I'm going to do the answers here in blue. So I just have to do 2 times that number, 2 times 0.0055. And this becomes 0.011. Now I need 0.01 down here, 0.01 minus 0.0055. And it turns out both of these answers are the same. They're going to be 0.0045. So that's your answer for H2 and I2. This is your answer for HI. And we're done. So there is, you can kind of see, I guess, where we're going to end up going with this. We will eventually end up having to do some quadratic equation ones. If the initial concentration of these two things is not the same, you don't really have an option. So that's kind of where we're headed. But for now, if you're paying close attention and you can find out these are equal, you might be able to use a square root to kind of trick yourself out of doing quadratic equations. So always look for those math shortcuts. Please be lazy. Work smarter, not harder. But that's about all we got for today's kind of introduction to ice charts before we get real tricky. So I will see you guys later for another lesson.